All right, we're going to estimate 1/12 integral from 0 to 12 of r of t dt using a midpoint sum. Oh, this must be a really popular question because we've done a bunch of these, haven't we? We did trapezoidal and Riemann. Now a little midpoint review. Okay, first, let's just do the area under the curve, which is what integration is anyway. Okay, popular AP exam question right here. All right, what is the area under the curve? Well, we don't have a function to integrate, do we, for the rainfall in Nashville? It was very erratic, by the way. Very jagged curve, so it's hard to write a formula anyway in nature. So use a midpoint sum. Okay, we've got a table. We're going from 0 to 12. It says use two subintervals of equal length. Well, 0 to 12 is the whole thing. So if I use two subintervals of equal length, I guess they want me to go from 0 to 6 and 6 to 12. That makes sense. All right, midpoint sum. Okay, let's see if we can remember this. The width of your rectangle, without drawing it, just looking at a chart, the width of the rectangle from 0 to 6 is base 6. Remember, you have to build the buildings and raise the roof? So this area is roughly a couple of rectangles. Base 6, 6 by what? All right, let's see. We've got a 0, we've got a 5.5. It's neither one of those. Midpoint sum. Go to the middle of 0 and 6, which is 3. Now see, if that had been 2, you couldn't have figured this out. I had to make it in the middle, by the way. That's mandatory. So the middle of 0 and 6 is 3, and that is associated with height 1. Y coordinates are height. So the first rectangle is a 6 by 1. Okay? Let's say you had like 0, 2, 3, and 6. You've got to use the 3. It's not the middle column. It's the middle number halfway between 0 and 6. Okay, 6 to 12. Width, base, 6. So plus 6 by what? All right, 6 to 12. Halfway between 6 and 12 is 9. 9 is associated with 6.8 in height. All right, so the area under the curve is roughly 6 by 1 is 6. Oh, there's a much better thing that you could do though. Couldn't we factor out the 6? Because it's a common width. Anytime you have a common width, I would factor it out. You get 1 plus 6.8. That's a little bit easier, all right? Equals 6 times 7.8. You know what? On a free response question, you literally can just walk away and leave it like that if you wanted to. I mean, they'll take it. They will take it. But maybe it's a calculator problem, okay? So I do want to point out one thing though. This is the part you can't forget. This is the integration estimation, but we never involve the 1/12, and students will forget that 1/12. It's actually 1/12 integral from 0 to 12. So let's put the 1/12 on the thing we just got. See, I was waiting for this moment here because the 6 and the 12 cross cancel. I want you to do this as a non-calculator test, so you know I'm going to give you something nice in there, right? As they often do on the AP test. And then if this falls on the calculator section, just hit a couple of buttons, you know, whatever. So 6 and 12, that's going to make a 1/2 times 7.8, all right? Okay, half of 78, and you put the decimal back in it, is one way to do it, okay? Half of 70 is 35. Half of 8 is another 4. So half of 78 is 39, but it's actually 3.9, okay? Or you could also do half of 7 is 3.5, plus another 0.4 is 3.9, whatever you want to do with your mental math tricks. So answer 3.9. Now, it says explain your answer. Explain it and use proper units in the process. Okay, what did we just do? Well, oh, wait a minute, this is a dead giveaway. When do you integrate from A to B and then divide by 1 over B minus A? Isn't this another average value? Which is why I showed you that in 7-1, and then I keep putting these in here from old AP exams. But I made it up my own, my own interesting problem with the rain. So that is an average value problem, all right? This 3.9 right here, it's the average number of inches that were on the ground in rain at any given time on that 12. It's not linear. So you can't just say 0, 7.2, oh, the middle of 0 and 7.2 is 3.6. So I guess the average rain on the ground that day was 3.6. No, it was actually a little bit closer to 3.9. It's a weighted average, okay? Because we spent a lot of time with a lot of rain on the ground. So it's a weighted, just like your grade is a weighted average, all right? You get more weight for summative category. So when you explain it, you need to put the word average in there, okay? Average value. Value means y, and y means cumulative inches. So don't put average value, put average cumulative inches, but it's the same thing. Average cumulative inches of rain at any time, let's say. Now they do like you to name intervals. You can't say any time during the whole day. How about any time on 0 to 12? That we do know. On bracket 0 to 12 bracket, okay? Anything remotely like that with the 3.9, they're gonna give you full credit on the AP test, all right? 3.9 average total inches throughout the entire day if you average everything. How about that? Interesting, right? Okay, so you've got a student riding their bicycle to school. And at time 0 is when they start, T is in minutes, and V of T on 0 to 8, that would be 0 minutes to 8 minutes, so I guess it took them 8 minutes to get here. The velocity is in miles per minute, and it is graphed with the piecewise function above. That's a piecewise function. Each little piece is put together. Every time they had to stop at a stop sign, and then they started again, and then they were going a certain speed, then they were going faster, then they were going slower, and it's just a bunch of piecewise madness, all right? That's a lot of different functions right there. Okay, is that picture the original function? Because that is going to make or break your understanding of this problem. Is that the original function? It says it's the velocity. Velocity is a derivative. But Mr. Wade, I don't see a prime on the V. It doesn't matter. It's F prime in disguise, okay? So this is equal to F prime, the velocity. And by the way, if there was any doubt, velocity is in miles per minute. Yep, it's a derivative, all right. Remember all the rate problems with the cone and the cylinder? So it is a derivative. This is the graph of y prime, not the original function y. That makes all the difference in the world. All right, number 1, find the acceleration at time equals 4.5 minutes. So 4.5 minutes into this student's ride to school, according to this graph, what was their acceleration? This is the first time we've formally done this in class, even though I hinted at it before. Acceleration is the double derivative in real life, right along with concavity. So we need to find basically F double prime of 4.5. All right, and it doesn't say estimate, it says find the acceleration. So that tells me we've got enough information to find it and not do some kind of, ridiculous estimate as we've done in the past. So F double prime of 4.5, I want you to understand what this is. The double derivative is the derivative of the derivative, all right? Isn't derivative a slope? Let's put slope of, it's really the slope of another derivative, isn't it? Wait a minute, hold on a second. Isn't derivative also velocity? Let's change that second derivative into velocity. Wait a minute. So the derivative of the derivative, or the acceleration, is just a slope of a velocity. Doesn't that make sense though? Tangent slope is the next derivative of the first derivative, which would take you to the second derivative. Okay, all you have to do, it's such an easy question. Look at the picture, find 4.5, which is going to be right here on this horizontal line, this flat bar right there, and figure out the slope of that little section right there. It's horizontal. The slope is 0. 0 watts, because it does say use correct units. They're going to get you if you don't put those units. Velocity is in miles per minute, so acceleration is in miles per minute per minute. Or a lot of places and a lot of people maybe in physics classes will put miles per minute squared, square minutes, okay? Either one of those is acceptable. Maybe that one's more common, but I'll take either one, okay? It is so simple to just realize that the double derivative or acceleration is the slope of the first derivative graph, the velocity graph. That's it, just that easy, okay? All right, second question. So we're going to integrate from 0 to 8 the absolute value of the velocity. Okay, this is a new twist. What does this even mean, right? Well, now hold on. We know integration means area, don't we? So it's the area under the absolute value of the velocity. Okay. Now, we don't have any equation over here, although linear equations are pretty easy to write, aren't they? All lines are y equals mx plus b. So if we could get the slope of each line and we could figure out its eventual y-intercept, you could actually write an equation for each one of those line segments. But wait, doesn't that seem like a lot of work? Okay, AP exam tip. If you have triangles or rectangles or trapezoids, you could even make some trapezoids like right here, okay? If you have rectangles, two trapezoids, triangles, semicircles, circles, shapes that you studied like in middle school, don't integrate to find the area. Just use the old formulas like triangle is 1/2 base times height, rectangle is base times height. So that's a huge tip for the AP exam. All right, let's find the area under the curve, not by integration, but by middle school math. But wait, it's the absolute value of the velocity. Now, what in the world does that mean? Would you just zoom in? It's the first time I've ever used the zoom, right? The absolute value of velocity? Wait a minute. Well, absolute value, what does it do? If you're above the x-axis and you're positive, you don't do anything. But if you're below the x-axis and you're negative and you take the absolute value, it folds it into a positive triangle, mirror image. So that's all it's saying. It's saying fold that up there, okay? All right, let's get to it. The first one is a triangle. 1/2 base times height. 1/2 base 2, height 0.1. All right, put that over here. This is not an estimate. This is exact, by the way, because it's linear, it's exact. 1/2 base 2, height 0.1. Okay, plus our new folded triangle, so it's no longer negative. 1/2 base 1, height 0.2. 1/2 base 1, height 0.2. All right. The third section, there's a triangle. 1/2 base 1, height 0.3. 1/2 base 1, height 0.3. You can see this is very, very easy. It's just tedious, right? But it's easy. They like giving you these tedious activities. It's like an Amazing Race episode if you ever watch that. Okay, it's like you have to go through all this crazy business, and it's not hard. You just have to stick with it, and then you succeed on the AP test. All right, rectangle, base times height, 1 by 0.3. All right, 1 by 0.3. Okay, that is a trapezoid. Base 1. Two different heights. You see that there? It's base 1 and it's the average of 0.3 and 0.2. All right, so it's a 1 by average of 0.3 and 0.2, so over 2. Plus one last trapezoid. Base, no, that's not the base. Be careful. See how these were parallel right here? These were parallel, so the base was the same, but the heights were different. This trapezoid, these bases are parallel, so that means the base is kind of this way. The base is actually 0.2, and it would be the average of 1 and 2. Okay, be careful. Average the ones that are different. Keep the one that's the same. So it's kind of on its side, right? If you look at it this way, now you can really see the trapezoid. So the base is 0.2. Be ever so careful here. Boy, this cord only goes so far, doesn't it? And then the average of 1 and 2, we said. So 1 plus 2 over 2. Okay? All right. Tedious, Amazing Race style, but we're going to get an answer here. And some students actually prefer to break up that last trapezoid into a rectangle and another triangle. Doesn't matter. You can break it up any way you want to break it up. No problem there. All right. So let's just crank this out as you would on the AP test. Half of 2 cancels 0.1. All right. Half of 0.2 is 0.1. Easy. All right. Half of 0.3, think money. Half of 30 cents is 15 cents. Okay? 1 times 0.3 is 0.3. All right. 0.3 plus 0.2 is 0.5. Half of 50 cents is 25 cents. Always makes so much more sense with money, right? So much more sense. That was actually unintended. All right. 3 over 2 right here. So let's change that into 3 over 2. And then let's cross cancel. 0.2 and 2 makes 0.1 and 1. 0.1 times 3 is 0.3. Okay? So there you go. All right. That's like 10 cents, 20, 35, 65, 90 plus 30 is $1.20 or 1.2. Voila. There's your answer. Now it does say explain your answer. What did you find and use correct units? Okay. We just integrated velocity, but the absolute value of velocity, which is going to be important. So if you integrate, wasn't the velocity in miles per minute, right? Turns out that if you integrate miles per minute, you just get miles. Now that makes sense. Derivative puts the per minute on it. Integration takes the per minute off. So that must be 1.2 miles. Now what else though? They do want you to explain a little bit more than that. Okay. If you integrate the velocity, you get something called displacement. All right, displacement. If you take a physics class, which I guess none of you have because we don't have AP physics here, that's too bad because all my calculus students used to also take physics and they would get a double dose. So if you integrate velocity, you get displacement. How far are you displaced from where you started riding your bike? Okay, just in case you decide to go back towards the house and then go back out again. If you integrate the absolute value of velocity, it takes all that driving backwards if you do that, and it puts it forwards into actual distance. So what we just did was find the total distance that the student rode on our bike. Now I can give you an example here. You see this upside down triangle? When the graph was above, you were actually going forwards towards school. When the graph was below, you were going back home because you probably left something at home, got back, picked up whatever it was, and then you started going forwards again, but faster because now you're late to school. So now it's steeper. Steeper means faster. And then as long as you're positive, you are going towards school, forwards, and then you end up stopping at time 8. You made it to school in 8 minutes, all right? Now, here's the deal. Because the bars were on there, we folded the negative triangle, and it was this one right here. It was the second shape, and we ended up with 1.2, all right? That is the distance traveled on the bike. 1.2 miles traveled by the student, okay? Total, you can even use the phrase total distance, that would be fine. Now see displacement. If you don't put the bars, then we would have not folded that triangle, and then this would have been a negative triangle, a negative 0.1. So if you end up doing minus 0.1 instead of plus 0.1, there's actually a 0.2 gap between those two numbers. You lose 0.2 and you end up with 1. What's 1? The displacement is 1 mile, but it didn't ask it here, but I'll probably ask it later somewhere, okay? The displacement, the student only lives 1 mile from the school. So how did they end up going 1.2 miles? Because remember, they went back to the house when they forgot something, so they did some extra riding on the bike that they didn't need to do because they were forgetful, right? Kind of like I am. My wife every morning, hey, you forgot your lunch. All right, so 1.2 distance traveled. Without the bars, it's just displacement. You are physically 1 mile from your house, okay? That is a big deal in physics and calculus that we've never talked about right there, all right? There you go. Final problem, D. All right, are you ready for a real hardcore calculus FRQ problem? All right, let's put your mind strength to the test. All right, Get ready, soldiers. All right, here we go. This is the true story of Action Park, an infamous and very dangerous amusement park that was poorly run in New Jersey. Take a look at the commercial.
There's nothing in the world like Action Park.
Come on down to Action Park in Vernon, New Jersey, where we feature the Cannonball Loop water slide, ranked the 4th most dangerous amusement park ride in the history of the world.
I love it here.
They've nicknamed us Accident Park and Class Action Park, but we really prefer Action Park because you know what? Local emergency room doctors, how do they know what they're talking about? We've averaged 100 serious injuries and 1 fatal accident every 3 years since 1978, and we're proud of it. And we're not going to close until they shut us down in 1996.
This is a great place to spend the day with your family.
So what if engineers designed roller coasters with elliptical loops instead of circular loops? You know what? We made the Cannonball Loop, which is a perfect circle, which means it's almost guaranteed to fracture your neck. Come on down to Action Park because we also have the #1 most dangerous ride in world history. Come join us. You'll probably leave in an ambulance.
I love Action Park because it's so beautiful.
Yes, I made up that commercial. But no, I did not make up that story. All those statistics are true. It was a complete disaster. I can't believe they let it run that long. Action Park was a real place. They did have 2 of the top 5 most dangerous rides in world history at any amusement park, and all that footage was real right there. So let me tell you, this is a true story, all right? So, comical commercial aside, first question, all right? First of all, the warm-up, they have 400 people standing in line at time 0. Very long line. We can't wait to fracture our necks on the circular Cannonball Loop, all right? You're not supposed to make this stuff a circle. It's supposed to be elliptical, all right? Talk to engineers. Now, the employees are able to add people to the line at a rate of R of T. Well, that's graphed over here. This is how fast they're adding people to the line, the R of T graph. Oh, so at time 0, they can add 800 people per hour, right? You'll notice this is in hours. So every hour, the employees can get 800 more people to line up. Then 1,200 after the first hour. Then after 2 hours, we've got lots of people showing up. Everybody can't wait. They hear all these screams and cries from the Cannonball Loop. Well, it's actually people getting hurt, but kids don't know that. They're like, oh wow, they're screaming over there. They must be having fun. So everybody starts piling in there and lining up, right? And then all of a sudden it kind of diminishes over time. People get tired of the long lines. And then it kind of flat lines. And then the park's going to close at 8 hours later. So then the line kind of diminishes and eventually they close the park. Thank goodness for good one day in 1996, right? So that's how fast people are being added to the line. Now, people are moving onto the water slide, which means they're being subtracted from the line at a rate of 1,000 people per hour. So they can quickly put people down that loop very quickly, one after the next, all right? So the graph is adding, R of T is adding to the line. The 1,000 people per hour is subtracting from the line, all right? How many people arrive from T equals 0 to T equals 2? First question on our FRQ, typical FRQ. All right, how many? How many is an amount, right? How many is an amount? How many times have we said this? Amount is original function. Rate, or speed or velocity, is the derivative. I'm looking for the original function, all right? From 0 to 2. Now, isn't this the arrival right here? This is the arrival rate. And then 1,000 is the subtracting from the line. We're only focusing on how many people arrive. So we're only focusing on R of T. But is R of T, is that the original function or the derivative? Oh, wait a minute, one little word. People at a rate of R of T. R of T, it says, is a rate. That's basically people per hour. This is a derivative. That's what you have to recognize on the AP exam, okay? We're really training for the exam now. Y prime, derivative, rate in people per hour. Okay, so here we go. How many people arrive from time 0 to time 2? I've given you the derivative graph, but you're trying to get back to the amount, which is the original function. There's only one way to get from the derivative graph to the original function. Integration. Okay? So integrate from 0 to 2. It's given right there. From 0 to 2 of the rate. The integration of the derivative shall be the original function. Fundamental theorem of calculus. Okay? And they want you to catch all that. Oh, rate. Oh, original. Oh, I integrate. Bingo. Okay. Now, do we actually integrate the equations? There are no equations. No. Remember, triangles, trapezoids, rectangles, just do the area under the curve. It's much easier. Area under the curve from 0 to 2. All right, 0 to 2. We'll draw this here. Let's split this right there, and you end up getting a trapezoid and another trapezoid. 2 trapezoids, actually. Okay, first trapezoid. Width, 1. 1 by what? Average height of 800 and 1200. 800 plus 1200 over 2. Okay, plus second trapezoid. Width, 1. 1 by average of 1200 and 1400. All right, using the trapezoidal rule, but it's not to estimate, it's to be exact this time, basically. The trapezoids are exact. Trapezoids are exact. Is that a blooper? No, just keep going. All right, so 800 plus 1200 is 2000 over 2 is 1000. Plus 12 plus 14 is 2600. Divided by 2 is 1300, and 1000 plus 1300 is 2,300 people. Oh, units, people. That's how many people show up to the line, just show up in the first 2 hours that it's open, okay? Question number 2, is the line increasing or decreasing in length from 2 to 3? A seemingly very simple question, be careful. Students will go over here from 2 to 3, they'll look at the graph and say, well, the line's going down, I guess the line's decreasing. Wait, hold on a second. You're in the wrong frame of mind, okay? Please be careful. This is the rate at which people are arriving. The rate at which people are arriving is going down, but does that mean the line is getting shorter or longer? Well, not necessarily either one. Here's the thing, okay? How are we adding to the line? We're adding to the line by the graph of R of t, people per hour, right? We're subtracting from the line at what rate? Steadily 1,000 people per hour. That's very consistent. You can't control people showing up to the line, but you can control how quickly you put them down the cannonball loop to their possible death. All right? So, when would the line actually be increasing? When the number of people showing up is outweighing or outdoing the number of people you're able to take away from the line and shove down the cannonball loop, okay? So when the rate of arrival is greater than the number of people showing up, the rate of people showing up, let's say. So this is the arrival rate, and this is the departure, the dearly departed, and that might be the case for some of these. They might be dearly departed and not make it through the loop alive. Okay, they've departed the line, they've gone down the loop, so down the water slide. So when the arrival can beat 1,000, the line will grow. When the people showing up is not at the level of 1,000, the line will shrink. That's what it's all about. Let's go over here. Draw yourself a bar at 1,000. You see 1,000 right here? Okay, that's the bar right there. From 2 to 3, notice what's happening here. 2 to 3. Even though the arrival rate is going down, the arrival rate is still above the 1,000. The arrival is beating the departure. The line is increasing. Okay? Understanding what's actually happening here. All right, number 3, part 3. This particular year that they had this on the AP exam. All right. Number 3, write an equation for the length of the line. Now, first of all, you have to think, is length a rate, a derivative, or is length an original function, a how much, an amount? Length. people, amount, how much. That's the original function. That's not the rate. It's how many people are physically in line. That's always the original function, right? So you have to write, let's say capital L, all right? The length of the line. How long is the line? Well, it would be this. It would be the amount, not the rate, but the amount of people that arrived, right? The amount that arrived minus the amount of people that departed at any time, right? If you have like the amount that got there minus the amount that got shoved down the ride, you would have the amount left over who are waiting in line. But there's one thing that I don't want you to overlook, okay? And it's over there, and students overlook it all the time. I'm going to take this thing off the tripod for the first time ever and go over here. Suppose 400 people were in line at the beginning when the park opened, or at least when this ride opened at time 0. Oh, students overlook that, okay? You have a plus 400 that were in the line to begin with. You know what that's like? It's kind of like a plus C. When you integrate and you realize, oh, I didn't have 0 rads of a radioactive element. I had 400 rads in the beginning, so I need to have that there. Okay, so people arrive, they add to the line. People depart, they subtract from the line, but it's all built on top of the original 400 people in line. That's so important. Okay, now let's calculate this. Okay, let's write a formula. How many people arrived? Well, we've got a graph, but that's the rate of arrival. How do we get from rate of arrival back to amount of arrival? Don't you integrate the derivative to get to the original function? It's the integration from time 0 to time what? Well, don't do times 8. It's not the length of the line at the end of the day. It's not the length of the line at time 3, time 4, time 5, time 6. It's the length of the line at any time. Go 0 to t, or 0 to x if you want. We don't know. Let it be any possible time. But we do know the park opened at time 0, okay? If you integrate the rate of arrival, so just put r of t right here, you will get the amount of people who arrived with a dt, all right? Minus how many people departed? Well, we know the rate of departure. Rate is derivative. 1,000 is the derivative. So from the beginning of the day until unknown time, the rate or derivative was 1,000. If you integrate 1,000, you'll get the physical amount of people that departed at any time, dt, plus the 400 that students often overlook. Forgetting that initial value is what that is, okay? You know what it's a lot like? Remember the hot air balloon? Remember we said that 16 feet was the radius gain, not the actual radius? You see, this part, the integration part, is the gain on top of the original initial value, okay? All right, now, final answer. L equals the integration from 0 to t. We don't know what the integration of this function is because it's like a bunch of different piecewise functions. We do know one thing. The integration of 1,000 is 1,000x, but today it's 1,000t. From 0 to t plus 400. Now, if you plug in t in place of t, you get 1,000t. Let me do a little side note here. 1,000t minus, if you plug in 0, you get 1,000 times 0. So, yes, you just get 1,000t, all right? So really, for your final answer, you don't have to write this. It's just 1,000t. Now, wait a minute. That makes sense, though, doesn't it? Isn't t hours? If t is hours, and they can put 1,000 people down the loop per hour, then after t number of hours or x number of hours or unknown hours, you would get 1,000 people times number of hours. That would give you how many people went down the slide. That totally makes sense. Okay, that's your line equation. Really thinking above and beyond what we've done this year and really putting it all together, right? These are pretty intense problems, but they make sense when you see them. They're not that bad, right? It's just different. Number 4, set up an equation that demonstrates at what time there is no longer a line, essentially. They asked this one year. It's so easy, actually, if you just think about it, okay? It's brand new to all of you, so you might think, I don't know where we're going, Mr. Wade. Check this out. This is the length of the line. At what time did the line finally stop growing? This is the equation of the line. At what time did the line no longer exist? Was there nobody in line any longer and you put everybody down the tube? Wouldn't that just be when the line equals 0? That's it. Or you could write all this stuff out too. But see, on the FRQs, if you've already defined capital L as something else, then you can write capital L in place of something else. Now, you can't write all this without the L and then just write L and assume they know what you're talking about if this isn't there. But if you've already defined it, you can write that. So all you had to do was write line equals 0. I mean, that's how easy it was. And finally, part 5, at what time is the line the longest? And then how many people are actually in line? Okay, when is the line the long? Oh, wait a minute. Calculus word longest. Longest is a maximum. You remember maximum way back in like August, September? A maximum is when you take the derivative, you do the number line test, and if you get a plus followed by a minus, it's a rise, fall, and it's a peak. A real life maximum. Okay, here's my line equation. Let's just do L prime, set it equal to 0, and solve it. That's it. Okay, take the derivative. Oh, here we go. This chapter right here, remember 7-1, the derivative of the integration is right back to the same thing. I mean, you can do like the capital I thing that we did before and all that, okay? But the derivative of the integration is just right back to R of t. You can trust me on that one. The derivative of minus 1,000t is minus 1,000, and the derivative of the original 400 people is 0, so it doesn't matter in the maximum part of the line. It matters the arrival versus the departure. That's what really matters. There's your derivative. Remember way back in the beginning of the year? We would set it equal to 0 and we would solve it. Add 1,000 to the other side. Tell me when R of t equals 1,000. We got a daggum graph right in front of us right here. When does R of t equal 1,000? Well, right there and right there. This one is above 3. And this one is linear, so it is right down the middle. It is actually right at 1/2. Okay? So t equals 1/2 and t equals 3. All right. But who's the maximum? Because one of those could just be where the line was at a minimum. That's also when the derivative equals 0. So one of those is the shortest and one of those is the longest. All right, AP graders are looking to see if you did a line. Did you label it L prime? Did you block it off from 0 to 8? Because outside that, we don't know what happened. The part closed. Did you put 1/2 and did you put 3, your landmines that you don't want to step on? Okay, now let's go right here. Let's plug in something between 0 and 1/2, like a fourth. Okay, what is L prime of 1/4? Remember you tested in the derivative? And it's this. It's R of 1/4 minus 1,000. Okay? R of 1/4. Let's see. Here's 1/4. Let's go up to R. It would be like right about there. Isn't that value lower than 1,000? So isn't lower than 1,000 minus 1,000 a negative number? Do you see it? Negative. All right? The line was shrinking or getting smaller until you plateaued above that 1,000 right there. Once you got above that, things changed. If you pick a number between 1/2 and 3, look right up here on the graph. 1/2 to 3. R is above 1,000. So the derivative R minus 1,000 is a larger minus a smaller, which is a positive. It's actually all sitting right there in the picture for you, okay? And from 3 to 8, from 3 all the way down to 8, the R graph was all below that imaginary 1,000 line. So that means R minus 1,000 is a lower minus a bigger number, which is negative. Turns out the plus minus is there. There's the verification. If you show them the number line, they will accept that. So the winner was at time 3, the line was the longest. And I just drew right through that. but it says, how long was it? Plug it back into your actual physical number of people in line right here. L of 3 at 3 hours past the opening time. I guess we don't know what time of day what that was, do we? Doesn't say. You would get 0 to 3, leave that R of t dt, but put the 3 there, minus 1,000 times t, which is 3, right there, plus 400. Okay. What's the area from 0 to 3 under R of t? Didn't we already do the area from 0 to 2 earlier? And see, they do that on purpose, and I did it on purpose. They do that so you can save time, because the AP exam, you get 15 minutes to do all this stuff, right? Just one free response question is 15-minute time span, roughly. We said 0 to 2 was 2,300 earlier, so use that number. So 2,300 is like all of this space plus 1 extra trapezoid. That is width 1 by the average of 1,400 and 1,000. And by the way, the average of 1,400 and 1,000 is 1,200, because the average is the middle when it's linear. So 1,200. I mean, the average is the middle anyway if you only have two numbers, all right? So it's a 1 by 1,200, not 12,000 if I said that, 1,200. So you end up getting 23 plus 12 is 3,500. So 3,500 people arrived in the first 3 hours, minus the 3,000 that they shoved down the line in the first 3 hours, plus the 400 people who were originally standing in line that add to it. And 35 minus 30 is 500, plus 400 is 900 people. And that's the longest the line ever got. And eventually the lines at Action Park went down to 0 and the whole place was paved over because it was atrocious. So go try the homework, see if you can try your hand at some of these FRQs on your own, because this is really what takes you from a 2 to a 3, a 3 to a 4, a 4 to a 5 on the AP exam. Being able to handle this stuff right here will raise your score, and I'm all about training you, okay? Try the homework. We will reconvene next time.
Hold it now.
FRQ problem. Gotta be able to rate it and just drop a marker. So the middle of 0 and 3 is, I don't like my x squared to be positive, to be negative, you stupid idiot. Well, this chart isn't even long enough. What the heck am I doing here? You stupid idiot. It's AM, not PM. You must pass 3.12. You must pass a 5.7. Oh, no, you can't, dummy. The flood, they call it now. What the heck do they call that thing?